Hello students, welcome to this lecture. In last few lectures, we have been discussing the exactly solvable models in quantum mechanics. We took our steps and we learned how we could analyze the solution of hydrogen atom problem. And now in this lecture onwards, we will start looking at more complex problems and how we cannot solve those complex problems exactly using quantum mechanical methods, and how and where we need approximate methods to solve these complex problems. But before that, we would do some basic discussion on such problems. One important thing that comes to help is to introduce this atomic unit system, because you would see that when we write down the Hamiltonian of a multi-electronic atom or a molecule, in those cases we would have many terms which would appear repetitively, but they have standard values. That is one. The other thing is that when we look at the energies that are coming from these microscopic systems, the molecular systems, we see that these energies are the magnitude of these energies are such that our regular SI units or CGS units are often very not adequate to explain those numbers. So it was felt that perhaps we should have a different unit system, and this unit system is called atomic unit. In atomic unit, some of the commonly used variables are kept have been given the value of unity. For example, like we have in our SI system, the mass or the length or time. So we have in atomic unit, the unit of mass is simply the mass of electron. All other masses, like the mass of proton, the mass of a nucleus, they all are expressed in the unit of electron mass, because mass of electron is one atomic unit. Its SI value is given over here. You can see this is 10 to the power minus 31 kilogram. So it's such a small number that if we use SI unit, life will become very difficult. So it is better if we use a different unit system that has a simpler value to write down or to communicate. So mass of electron is considered as the unit mass in atomic unit. Similarly, the charge of electron is one unit charge in atomic unit, whose SI value is given over here. Of course, the charge of electron is negatively charged. So this has when you are expressing it as an electron, we would simply say it as -1. When you call it a positively charged particle, then we will express it as plus and in the units of electron charge. Like we have in our SI system or CGS system, the unit of time, here also we have unit of time in atomic unit, which is expressed roughly the time that it takes for an electron to revolve 1s orbital of hydrogen atom, which comes about to be 2.419 into 10 to the power minus 17 second. So you see in SI unit this number is quite small. We can of course express it in terms of attosecond unit. Attosecond is simply 10 to the power minus 18 seconds. So in that case, the atomic unit of time falls as 24 attoseconds. As the other commonly used quantity is h bar in quantum mechanical system. So that's why this is h bar is kept as 1. Which is h divided by 2 pi. So therefore, the Planck's constant becomes 2 pi, because we are defining h bar as 1. So these are some of the definitions that we are putting forward. The unit of length in atomic unit is expressed by the Bohr's radius, which is 0.53 angstrom, or you can see this is expressed in 10 to the power minus 11. You can also express it in terms of picometer or angstrom units. The energy is expressed in terms of Hartree, that is the atomic unit of energy, which is given, which is the symbol we use is EH. The Hartree atomic unit you see it is expressed in the units of joules. If you remember, if we express this Hartree unit in terms of electron volt, it would simply come out to be 27.212 electron volt, which is actually twice the energy of hydrogen atom. So, if you remember, the energy of the hydrogen atom in its ground state was minus 13.6 electron volt, which is essentially minus 0.5 atomic units of energy. So, the minus sign indicates that the molecule, the atom is stable, that is there is an attractive interaction between the electron and the nucleus in the hydrogen atom. That signifies that justifies the presence of minus sign, but the unit of the energy is if we express hydrogen atom's energy in atomic unit, it would be minus 0.5 atomic unit. Similarly, other constants like speed of light we can express as here. The fine structure constant, which is given over 1 over c. The other quantity that we would be using even in this course is the Bohr magneton. When we express, when we study the effect of external magnetic field on our energy levels, then we would come across this Bohr magneton. You see, Bohr magneton's relation is given by as E h bar divided by 2 me. And if it is E is the charge of electron, h bar is so therefore this is 1, h bar is, we have defined it as 1 divided by 2 mass of electron. So, mass of electron is again 1 in atomic unit. So, therefore, Bohr magneton becomes 1 divided by 2. So, that is 0.5 and its SI units I am sure you are all aware of. Like Bohr magneton is expressed for the electron. When I am talking about the nuclear magneton, I simply replace this relation E h bar divided by 2 me. The me, the mass of electron, is replaced by the mass of proton to get the nuclear magneton's value in atomic unit. And since we know that the mass of proton is about nearly 2000 times heavier than the mass of electron, so therefore you see the nuclear magneton is about 3 orders of magnitude less than the Bohr magneton. Vacuum permittivity is another constant that appears in the Hamiltonian. So, when we are expressing the interaction between electron and nucleus or the interaction between electron, so we express them as Coulombic interaction. So, in those expressions we often see 1 over 4 pi epsilon 0. So, these quantities appear often. So, if we make them as unit, of course, they have their SI values. Then in that case, if we are writing down the Hamiltonian in atomic unit, the expression becomes very simple. Similarly, vacuum permeability is also shown here. Now, we have seen this atomic unit, and let us use this atomic unit to write down the Hamiltonian of a molecule in general. So, when I talk about the Hamiltonian of a molecule, I see that I have several nuclei, because a molecule is ideally composed of many nuclei, and of course, each nucleus would have each atom would have several electrons. So, therefore, the molecule would also have several electrons. So, now my system is a multinuclear, multi-electronic system. Now, for such a system, if I want to write down the Hamiltonian, I already know that Hamiltonian would have 2 different contributions. One would be from kinetic energy, the other would be from potential energy. And now, each particle in my system would contribute to the kinetic energy, because each particle with a mass would have a kinetic energy. So, therefore, if I have capital N number of nuclei, if I have small n number of electrons, then I have those many number of kinetic energy terms coming from nuclei and electrons respectively. So, the first term in this expression, the Hamiltonian expression, shows minus 1 over 2 ma, the Laplacian corresponding to the nucleus. So, nucleus is signified is given as with the index a, where a goes from 1 to n, capital N. So, that means if I have capital N number of nuclei, then I would have n number of kinetic energy terms coming from each of those each nucleus corresponds to contributes to 1 kinetic energy. So, therefore, I have in total n number of capital N number of kinetic energy. And here you see the mass of the nucleus is kept within the summation, because I would have in a molecule I would have different atoms. Suppose I have hydrogen atom, oxygen atom, each of them would have different atomic mass. So, therefore, this mass of the atom is kept within the summation. So, this is the nuclear kinetic energy operator. Now, the next term that you see are the next term has two terms within it. So, let us understand each of them carefully. The first term over here, this term corresponds to the kinetic energy of the electron. I have small n number of electrons in my system. So, therefore, I have small n number of kinetic energy terms arising from these electrons. This Laplacian of corresponding to each electron is given by this nabla sign. So, this is simply second derivative with respect to the coordinates. So, d square by dx square plus d square by dy square plus d square by dz square in Cartesian. So, this Laplacian is the operative part of this kinetic energy operator, and my regular expression of the kinetic energy has minus h bar square divided by 2m. So, you see h bar is already kept to 1, that is because I am writing it in atomic units. So, same also over here for the kinetic energy of the nucleus. And one thing that you should notice that there is no mass term here, whereas when I was writing down the nuclear kinetic energy, I had a mass term. The reason being that in atomic unit the mass of electron has been kept to 1. So, therefore, I do not have this mass term over here. And now this term is repeated small n number of times. The second term, when you look at, you would see that first of all there is a negative sign, and this is a potential energy term. What is this energy talking about? So, this is actually the interaction between a nucleus A and an electron I. So, if I have capital N number of electrons, capital N number of nuclei. So, I have this A goes from 1 to n. Each nucleus in my molecule can interact with every electron present in my system. So, therefore, I have small n number of electrons, capital N number of nuclei. So, total small n multiplied by capital N number of electron nuclear interactions. This RIA is the distance between an electron I and a nucleus A. ZA over here is the nuclear charge of the atom A. So, these terms to get the electron kinetic energy term plus the interaction between an electron and nucleus, these are called one electron terms, because each term corresponds to an electron. Of course, the second term also talks about nucleus, but we will come back to that. But at least so far as electrons are concerned, each of these terms is contributed from one electron. Now, let us look at the next term, which is essentially electron repulsion term. So, you see, if I have n number of electrons, so I can have each electron interacting with every other electron. So, each electron would interact with n minus 1 number of electrons. So, therefore, I would have n into n minus 1 divided by 2 number of electron interaction in this term. And finally, we come to the last term, which is the nuclear repulsion. So, which is given by the nuclear charges of atom A and atom B, which this is and the distance capital RAB is the internuclear distances. So, now we see that the first term is kinetic energy of electron, kinetic energy of the nuclei. The last term is the nuclear repulsion. The middle two terms are electronic terms. The first one over here is the kinetic energy of electron. This is electron nucleus interaction energy, and this is electron interaction energy. Now, what happens is that when you try to solve this problem quantum mechanically, one important approximation we make is the so-called Born-Oppenheimer approximation. The idea behind Born-Oppenheimer approximation is that the mass of electron is very small compared to the mass of the nucleus. So therefore, when the electrons are moving around, the nuclei are essentially more or less static. So therefore, since they correspond to such different dynamics, so therefore perhaps we can separate them from each other. So we can decouple the electronic degrees of freedom from the nuclear degrees of freedom, and essentially what we say is that when you are solving the electronic degrees of freedom, we can assume that the nuclear degrees of freedom are all frozen. So as if the nuclei are frozen, and in those frozen nuclear condition, we are trying to solve the electronic part of the problem. So this is essentially the Born-Oppenheimer approximation. So what do I mean? What do I get here? That I say that the when I am solving the problem, the molecular Hamiltonian, I say that the nuclei are not moving. So therefore, the kinetic energy of the nuclei goes 0. And if the nuclei are not moving, so that means the distance between them is fixed. So if the distance between them is fixed, so this term becomes a constant. Now I have the first term becoming a 0 within Born-Oppenheimer approximation, this last term becoming a constant. We know that if I have a constant term in my Hamiltonians, I need not worry about that. I can simply solve the remaining part of the operator, and the eigenvalues that I would get, I can simply add this constant later on. So that would also work. So this Vnn is a constant, and the kinetic energy of the nuclei becomes 0. That leaves me with these terms which are called as the electronic Hamiltonian. So this is my molecular Hamiltonian, which has the kinetic energy of the electron as well as the nuclear repulsion. If I exclude these two terms, what I am left with the so-called electronic Hamiltonian. Of course, often what happens is that when you solve this electronic Hamiltonian, you also add afterwards this Vnn, which is a constant to this. So therefore, when you consider the energy that I am getting out of this electronic energy, in some cases, oftentimes we also include the nuclear repulsion into this, because this is simply a constant. This is the Hamiltonian that we are getting for a molecule. Now, if I have a multi-electronic atom, so just one atom, that means one nucleus, and I have many electrons, unlike hydrogen atom. In that case, this capital N becomes 1 because I have got one nucleus, but the small n is as depends on the atom that I am considering. So that will be the number of electrons in that atom. Suppose I am considering helium atom or lithium atom, so therefore I will have 2 electrons or 3 electrons to consider, whereas the number of nuclei will become 1. But in case of molecule, I have multi-electronic as well as multi-nuclear system. So we have this Hamiltonian in our hand, but now the thing is, when I am looking for a molecular system or even a multi-electronic atom, I have this 2 electron part. These 2 electron operators which create trouble in getting exact solution of the Hamiltonian operator. As long as I have system which depend only on one electron operator, so like these terms, one electron operators, I can solve such problems. But the moment I have electron-electron interactions, that means 2 electron operators coming into a picture, I fail to solve the problem exactly through quantum mechanics. Now, in those cases, we would use some approximate methods, and that is what we are going to discuss next. The first method that we are going to discuss, the first approximate method that we are going to discuss is the variational principle. what does variational principle tell and how we can use them, this principle to solve quantum mechanical problems? That's what we are going to discuss next. Variational principle is quite simple in its statement. It says, suppose this is what we normally would want to have. If I have a system, I know how to write down the Hamiltonian. This is what we discussed. If I know its ground state eigenfunction, that is psi 0, I can simply write this down. So, where psi 0 is the ground state eigenfunction, that means the solution of this Hamiltonian. So, if psi 0 is the eigenfunction of Hamiltonian with energy E0, then I would get the expectation value of Hamiltonian as single value of E0 without any uncertainty. But this is the case when I know the exact solution of the Hamiltonian. But often times, as we have realized, whenever I have more than one electron, I do not know the exact solution. In that case, when I do not know the exact solution, suppose so that means I do not know the form of psi 0 or the value of psi 0, the wave function which contains all the information. So, when I do not know psi 0, what variational principle tells me that why don't you try with another trial function. So, this phi that you see over here is a trial function which is being used in place of the exact solution, because we do not know the exact solution. When you do not know the exact solution, we are making a guess. Now, this guess function is phi. It can have any form. We will have some condition imposed on this phi as we discussed, but at the moment let us keep this in mind that we are just making a guess on the wave function. So, if I made a guess on this, since I already know the Hamiltonian of the system, I can evaluate this integral either analytically, or if analytically evaluating that integral is difficult, at least I can do that numerically using a computer, or it would be somewhat straightforward. So, I obtain this expectation value of the Hamiltonian operator with respect to this trial guess function phi, and divided this by overlap of this phi. So, if this trial function is a normalized function, if I have normalized this trial function, then you would see the overlap of phi with itself becomes 1. So, this left hand side, which is the expectation value, the energy value, when I am making a trial function as phi, would be given as this energy integral. Of course, evaluating this energy integral is straightforward. What variational principle guarantees me is that no matter what phi I choose, no matter which trial function I choose, the E phi, the energy that I would get out of this operation, is always going to be greater than the real value of the energy. The ground state energy E0, which is expressed over here, it's always going to be greater than E0. At best, it can become equal to E0, but it can never become lower than E0. So, that means variational principle gives me an upper bound to the ground state true energy. And it also tells me that when the wave function phi, the trial wave function phi, approaches the real solution psi 0, in that case the energy E phi would also approach E0. So, that means I have now a way to find out whether my trial wave function is working or not. How do I do that? I would see that if my energy E phi approaches E0, which is the real energy, in that case that means the trial wave function is actually a good description of psi 0. But in many cases I wouldn't know what is the value of E0. So, how would I ensure that E phi goes to towards E0? This is where variational principle comes to help, because variational principle tells me that do not worry as to what happens to the energy. You try your best to minimize this energy, because you can never get E phi as lower than E0. It would always be greater than E0, or at best it will become equal to E0. So, therefore, I can go on minimizing this E phi until as best as I could, and the best outcome of that, the minimized value of the energy E5 would actually be my best energy that is coming out of this trial wave function. In this lecture, we discussed about the concept of variational principle, how it is justified, and what are its consequences are the topic of our next discussion. Thank you for your attention.